Okay, can you hear me?
Yes.
Hi, everyone. Good morning, good afternoon, or good evening, depends on your time zone. Welcome you all to the Weyprecht lecture of the SCA Open Science Conference 2022. I'm Yedong Kim, the president of SCA. Before we start, I have a couple of housekeeping announcements. The question will be followed, question and will be answered following the lecture. And please use the Q&A box below your screen. And if you have a question, also SCA Secretariat keep monitoring the chat box during the session for any help during the session. And also I'd like to let you know that considering the audience is in different time zone, this session will be recorded to be made available to registered participant in the past event section of the front page. Also, I think it's all relevant to the lecture of today. We'll upload the recording also to the SCA YouTube channel at the conference. If presenter, if you do not like to present to be available on YouTube, just to let us SCA know by the end of next week. Okay. As you know, the Weyprecht lecture is one of the most prestigious lecture the SCA provide at the biennial Open Science Conference for delivering the most pressing scientific issues in the Antarctic and Southern Ocean. This year, SCA is proud to invite Professor Sophie Nowicki as a Weyprecht lecturer. I believe if you now stay in the Northern Hemisphere, you are suffering from unprecedented heat wave that is believed to be related to ongoing global change. We also observed the huge heat wave in the interior of Antarctic last March. The temperature rose 40 to 50 degrees Celsius, higher than normal in some places in the Antarctic. The warming in the Antarctic could bring ice sheet melting and consequently cause sea level rise. This is an urgent issue that we, polar science community, should provide expectation related to sea level rise and climate change and to the public. I think it's very timely and fortunate that we are able to have Professor Nowicki today to present to us this important issue of Antarctic ice sheet and climate of our time. I may briefly introduce Professor Sophie Nowicki, who will give a lecture titled as Understanding and Projecting the Antarctic Ice Sheet, a Community Challenge. Professor Nowicki received the bachelor and master degree in remote sensing and image processing from University of Edinburgh, and she moved to University College London and got PhD in theoretical glaciology. Then moved to NASA Goddard Space Flight Center, worked for more than 10 years as a research scientist and deputy chief for the Weyprecht Sciences Lab. In 2020, she moved to the Department of Geology at the University of Buffalo as Empire Innovation Professor. Her research focused on the Greenland and Antarctic ice sheet, their connection to the Earth's climate system, and the impact on sea level. Dr. Nowicki has been involved in various international programs, including World Climate Research Program, International Association of Weyprecht Sciences, and ice sheet modeling intercomparison project. More importantly, she was invited to be a lead author on IPCC 6 report, assessment report, chapter on ocean, cryosphere, and sea level change. No further introduction. I'd like to invite Professor Nowicki to the floor. Sophie, the floor is all yours.
Thank you very much for this invitation to present this very important lecture. I will steal the screen and start sharing. It's really a big honor actually, because the first time that I actually we want to do it this way. The first time that I went to SCAR was the first year that this lecture was given in 2008. So it was really nice for me to kind of realize and make the connections. But before I start, I really wanted to thank basically all of my co-authors, which are many, many, many. And this presentation really and those thoughts is the results of course, my own thoughts throughout my career as a researcher, but it would not have happened without the CRS community, the INBI community, which is observational based, and the ISMEP6 participants, which are shown, some of them are shown in this wonderful photo. Well, let's go straight to the point. As was mentioned, I got the great honor to be invited to be part of an author for the latest IPCC assessment that came out a year ago. And we made the statement as authors that the Antarctic ice sheet will continue to lose mass throughout this century under all emission scenario, and this is one of the key figures that the chapter has. But when you want to so I wanted today to kind of go into how we got to that figure and how it can be improved. That's really the goal of my presentations. The bulk of the message to some extent is that right now the projections that AR6 made are in a way very similar to the previous IPCC report. That's the key message to take. And I think it's, despite all of the improvements that we've made as the sheet modeling community, the fact that those projections are quite similar in terms of range is because, in a way, a lot of the climate forcing that were used to make that figure were the same as previous assessment report. We'll go into that, but that because there is basically one of the issues that we have to face as a community is that the climate modeling community needs to be much more cognisant to the ice sheet modeling community that needs time to make projections. Otherwise, we have to use previous forcing from previous IPCC reports or previous CIMITs to match up projections. Key to the IPCC report, and I also wanted to kind of say is that, of course, it's not just, IPCC report coming to an assessment of all the available literature. And so there is a large contribution of ISMEP6, an effort that I've been heavily involved for the last many, many years. There is also a good computation about emulator of ISMEP6, and we'll go into this. It's basically the idea that it takes a lot of time for the ice sheet modelers to make a certain number of scenarios, and emulators is a very powerful way to cover many, many, many future possible climates, and learn from those expensive ones and cover all of your bases. And then you had this other main effort called LARMEP, which were used to make those projections. But how did we get there? Really, the IPCC reports have a big influence on what we do as a community, or for me, as I do as a community, that drives my work. And when I finished my PhD, this was the fourth assessment report had just come out, and had this statement that said that the understanding of the effect of the very rapid dynamic changes that have been observed over the ice sheets was too limited to really assess the likelihood in ice sheet models or to provide a best estimate for upper bound of sea level rise. And that statement for the ice sheet community was not a wake-up call because people were working a lot on those, but it was really kind of saying, look, the ice sheet models, they don't really do much. They don't, in terms of projections, there's not much sea level coming. They don't capture what the observation is showing. And that triggered a lot of research for many, many years. One of the research and one of the efforts that kind of was triggered by this statement was the SCAR workshop that I've kind of highlighted here. The SCAR ISC Chris's workshop on improving ice sheet models in July 5th to 7th, 2008. So there was a SCAR conference in Russia. My first time that I went to a SCAR conference. It was an amazing event, and I really, wish for all young, because I was just finishing my PhD, so I was an early career scientist. For any early career scientist, if you have the opportunity to go to those types of workshop, it's a really amazing way to kind of build your network and get to know people. So for me, this workshop was really important because met, of course, a lot of people that are going to be crucial in my career, but it also changed the way that I was thinking. I used to have done, and I had spent the 4 years during my PhD trying to understand the grounding line, a very simple problem, well, not simple, but a very narrow problem in a way, because it's just like one point between the grounded ice sheet and the floating ice shelf and how it behaves. And I was doing it from a theoretical point of view. So it was, my brain of thinking was 4 years of thinking about that way of modeling this one transition zone, to then basically this workshop about how you make projections with ice sheet models. And I realized that, oh my God, all that I was focusing on the last few years actually was not really relevant for that community trying to make projections, because they couldn't even worry about the kind of scales I was thinking about. So being forced to go to workshops where you are maybe not what you're doing is for me, was very beneficial and helped me to kind of broaden my knowledge and my thinking. But so how did we get there? The ice sheet modeling community, of course, has been really good at benchmarking models and improving models and testing them against each other. This is just like a small summary about where we got there. I mean, the earliest stage, the ESMIP, which is the European Ice Sheet Modeling Intercomparison Project, where I've put the abstract, is one of the first one, like benchmark for testing ice sheet models, where there's a series of benchmark that we still use, right, that ice sheet models have to do and that we have to compare. And then came basically, of course, at that time in '96, most of the ice sheet models that we're using were doing simple approximation of shallow ice, so they were not therefore able to kind of do those rapid changes that the observation was showing us. That motivated, for example, this 2008, the ESMIP home, which is the higher order and full Stokes model experiments, which then was followed by ESMIP Heine, which is inherent event. So and then which was followed by the MISMIP series, which is the Marine Ice Sheet Model Intercomparison project, which kind of focused really on like instabilities due to the grounding lines, which was triggered by even more MISMIPs and looking to the ocean and ... Right. So a point that I want to take about is that as a community, the ice sheet modeling community, they sometimes get a bad press and criticize that our models are not good enough. But actually, if you kind of dig around in what we do, all of the models that we are using have been benchmarked. We rigorous testing. You cannot really get a new model without showing how well you compare with all of those history. So it's really my plea on kind of saying, or the realization that as a community, we've been very open on what we can do and always trying to improve. The one I'm really looking forward to that's happening right now is this calving myth. We now, of course, understand that calving is super important for ice sheet models and can lead to big, lead to large sea level rise. It is something that our models are still struggling with, and that's why this calving myth is very important. So as an early career scientist, taking part in those kind of efforts is also very, it takes a lot of time, of course, but you will learn a lot and get to know and improve your network. So following this, at this CLAR meeting that I was in 2008, I was basically introduced to this sea rise effort, which was led in the US it was open. Any ice sheet modelers that could want to take part in the effort could take part, and it was trying to make some type of projections for AR5. It was community driven. It was led by Bob Schneider, and when I moved to Goddard, this was one of the projects I worked on, where basically we were, it was the first time trying to really make projections related to some climate models. And this is when we didn't really know what we were doing as a community, and we were trying our best. And so we said that we're going to take all of the CMIP models together, make the average. This is what I'm showing with that curve, mean surface temperature anomaly for Antarctica. And then we had mean precipitation anomaly in gray, and we gave the data sets to the ice sheet modelers. And then we had a series of experiments. We were going to look at the climate forcing, which was basically simply applying those. C2 was making it 1.5 times, and C3 was doubling those atmospheric forcing. We had a series of melting experiments, which was 2 meters per year for M1, 20 meters per year for M2, and 200 meters per year for M3. The idea for this M3 melting experiment, crazy forcing that would never really happen, right, 200 meters per year, it was trying to kind of look about how much ice could really be kind of taken out from Antarctica. And so you can see, right, that melting is a way that you can get rid of a lot of ice. So in any point, the point of sea rise is that it really made me realize basically the power of community effort. All those models came with their strengths and weaknesses. All of those models were tested. All of those models behaved differently. And it was very hard to know which one was best. And that's why this kind of community effort about how do we try to make a projection, I learned a lot, and it led to a lot of my future work. One of the items that really serialized for me is the fact that, you know, after we had tried to do experiments of like fixed melt rates, which made no sense and were really hard to explain, it made me realize that really in terms of projections, we had to be better connected with the climate community, because we had to really have basal melt rates that were linked with the climate models. And that's where ISMEP6 came from. It was a combination of sea rise and nice to see the European effort at that time. It brought all of the ice sheet modeling communities together internationally. It was sponsored by CLIC, which was very important because it kind of helped us, give us some motivation to try to work together. And it became a long story that was for me a pretty full journey. This was the first workshop where we debated, like, shall we try to do projections as a community or not? Are we ready? And the question, are we ready, is a fair question, because of course, you know, models are still having issues, and therefore, will you ever be ready is a fair question. We spend a lot of time as ISMEP6 as a group to think about climate model and climate forcing. This is an example of all of the, basically that timeline that I'm showing with the Star Wars, the first workshop. And then we had to deliver everything by December 2019 to be considered by the IPCC on time. And so basically that whole dotted line here is how long it took to kind of think about how to select CMIP models and scenarios. What can we ask? What do the CMIP models need to have? How many forcing simulations can actually models do? Yet, tons of questions. The blue and the green dotted line were a focus group thinking about atmospheric forcing or ocean forcing. So when you try to think about, when you look at these ISMEP6 effort or any kind of projections, a lot of time goes on thinking about what we can do and what we need to do and getting those forcing ready. We have protocols described in many papers that are highlighted here. But the point here is that we selected a lot of models that were, in the end, CMIP5 driven, just because by the time that we were trying to do, you know, remember we have a deadline for IPCC that needed to be papers being submitted and published. And basically the CMIP6 models were running late. And so even though we wanted to be closely related to CMIP6 in terms of forcing, we couldn't do any evaluation because there was no CMIP6 models to evaluate. That's why a lot of ISMEP6 is based on RCPs and CMIP5. We spend a lot of time developing new parameterizations, which are of course motivated by observations. And so ISMEP6 developed two parameterizations, the meet and method and the Pine Island Glacier method that had much stronger melt rates around Pine Island Glacier. And all were basically, both parameterizations have basically coefficients that we don't really know, some unknowns that we don't know, that were identified using observations. But that's basically what I mean. It takes that long from 2015 to present, you know, to many years to get some kind of forcing. Is basically thinking of those kind of parameterizations and how to improve. Who took part in ISMEP6? Basically, it was open to everyone in the world, all of these ice sheet models, and we had actually contribution from everyone, or most of the community, which is very important because, as you can see, the current ice sheet models, they really differ in terms of numerics, the way that they choose to resolve stress, how they have the resolution, spatial resolution, and all ways that they do items like basal melt parameterizations. What did we get in terms of result with ISMEP6? This is basically the CMIP5 projections, and I'm comparing them to AR5 and to the ESROC. The key point is that there is always a spread, like different ice sheet models are going to respond differently. Okay, fine. The different colors are different climate models as drivers. And what I really want you to kind of take away is that a lot of the uncertainty that we face and a lot of the spread that we face in the projections is actually linked to the CMIP models that we use for future drivers and future scenarios. And for me, if this is one thing that you take away from this presentation, is that improving polar climate is really where we need to move as a community. There are, of course, regional differences. This is again for the RCP 8.5, my different climate models that took part. And this is the projections from ISMEP 6, when you're doing all over 13 participating ice sheet models. And so you can see that in general, West Antarctica, of course, will lose mass in the future, unless it's driven by climate that SARO or EPSL predicts. East Antarctica is a bit more tricky. In some simulation, it loses mass, and then in others, it actually gains mass. And that's because in an increased warmer world, you may have basically increased accumulations and snowfall, which causes the ice sheet to grow. And that's basically the story of Antarctica, and why it's so hard to make projections, is that on the one hand, you have the mass loss from the West Atlantic ice sheet that's driven by the ocean, that is basically kind of counterbalanced by the mass gain that East Antarctica can get in a warmer world due to increased accumulation. That's what those diagrams are showing here too. It's basically, if you're comparing different scenarios, you have this balance where sometime, here we're looking at Antarctica, sometime you have basically mass loss dominates, so you have more mass loss under higher emission scenarios. But sometimes you also have some climate model that projects that accumulation dominates, where you have more mass gain on the high emission scenario. For East Antarctica, again, it's a very, very complex picture. And so when you try to add those two numbers together, maybe they tend to kind of cancel a bit. And that's why we're having a really hard time getting, first of all, scenario dependence in Antarctica, and also those large numbers of sea level projections, even though those two ice sheets can lead to very large numbers. The bottom plots are the emulators that Thompson Edward did based on the ISMEP 6 simulation. It does show that basically different scenarios where this SSP 1.19 is a low emission scenario, SSP 585 is a high emission scenario. So you do see that there is basically under warming world, and West Antarctica will basically lose more mass, but then East Antarctica in the warming world can basically gain more mass because of this balance of accumulation. So what is behind, therefore, the AR6 projections? We have to take everything as an IPCC author that's available in the literature. I cannot say that given that I've been involved with ISMEP 6 for such a long time, I give preference to that. This is really out of the question. I have to be really fair to what's going on. And so basically there's, of course, ISMEP 6 projections that took part in this, but there's also this other community effort called LARMEP, which is the Antarctic linear response to Antarctic contribution. It's basically basal ice shelf melt using linear response functions, and then it's basically ocean on as an effort. And then because it's an ocean-only projections, it meant that as an R6, we basically had to estimate surface mass balance to kind of add that to, because, you know, future Antarctica is both due to the ocean and the surface mass balance. And so that's why IPCC had to basically add this surface mass balance component. And that's how we basically combine those and other literature and other papers in the literature. And we combine, you know, as an IPCC projections, we combine ISMEP 6 emulated and LARMEP to give those numbers, the medium confidence number, which are, as we said at the beginning of my story, that they're very similar to previous assessment report. But what AR6 did was also something a bit different this time. We also acknowledged the fact that there is a likelihood in red of a much higher emission scenario. This comes from other lines of evidence. It comes from the SCG, which is the Structured Expert Elicitation Methods. So it's led by Jonathan Bamber, and it's curing experts about what they think the future could be. So it's kind of trying to kind of sample what we know that we don't know, or what we don't know that we don't know, but basically something that we know that the models can't capture. And then we also have projections from MICI, the marine ice cliff instabilities, that give possibility to much more higher sea level. In addition, what AR6 did, they also used the ISMEP6 ABUMEP, which was an effort that tried to simulate the collapse of the West Antarctic ice sheets due to the marine ice sheets instability. And basically we kind of remove all of the ice shelves and then let the ice sheet go. And it kind of shows that, yeah, if all the ice shelves go, you can have an instability and you can have very high sea level numbers. So those all kind of came together to make a storyline in the IPCC report that you can try to understand what could cause higher sea level, and the fact that, you know, we cannot rule out those higher numbers. And that's how we came to basically those statements in the IPCC report that you have deep uncertainty that persists with respect to the possible evolution of the Antarctic ice sheets along high mass last storyline within the first century due to those instabilities. And that's how we came to those large numbers. Right, so now how do we move on? We model what we know. And how do we move on? I mean, if you think back, of course, observations are crucial. This is what Antarctica looked like when my grandmother was born in 1900. This is what Antarctica looked like when my kids were born. And so in 100 years time scale, we've learned so much thanks to the satellite observations and all of the field work that people did. So this knowledge that we know from observation is really, really key. However, as a modeler, sometimes observations are sometimes really challenging to use because even though there is tons of wonderful work being done, this is a plot from IMBY paper. And in here in green, this is basically gravitometry. So you're thinking about one type of satellite that measures the mass loss using gravimeters, and different estimates. Those different boxes are different published numbers in the literature. At the same time, you also have laser altimetry, which measures the height of the ice sheets, which again, different people giving different numbers. So as an ice sheet modeler, this kind of plot is a bit of a problem because I have a huge range. And so which one do I use? So those efforts, community efforts that IMBY did, you know, it's kind of really boring in a way to kind of to contribute to this because you're giving all of your hard work. You might have to change your data. So for the participant, it's not very interesting, but it's really, really important because it reveals that maybe those differences are due to different ice sheet mass, for example, or different assumptions that somebody made. And so when you reconcile those mass change for Antarctica, it becomes the original IMBY plot, that mass loss, it is much more powerful and much more useful to have a consensus estimate for me as a modeler in order to use. So IMBY was followed by IMBY2, and now there is IMBY3. Now, there is still an issue as a modeler. This is great. I know that Antarctica is therefore losing mass, and I know that my ice sheet models maybe have issue reproducing this. However, this mass loss here, what is tricky for me is that it's a combination of surface mass balance, basal mass balance, all of those processes that you know that are happening. And this doesn't really tell me, it tells me that the ice sheet is losing mass, but it doesn't really tell me what caused this mass change. And so I'm really hoping that with IMBY3, there might be a bit more work on trying to basically identify how much of this mass loss is actually due to surface mass balance. Those are things that will be discussions, hopefully that will come from the ice sheet modeling community talking to the observational community. You can also argue the fact that, okay, well, to have higher mass loss, we've kind of seen that from sea rise, of course, is all linked to the forcing. I really believe that. And so since ISMEP6, there has been more research about how to improve those forcing. This is an example about how much does changes in atmospheric forcing could affect the projections. So they're comparing what ISMEP6 did, the surface mass balance for ISMEP6 derived directly from a climate model. So on the top is basically driven by one of NORISM. At the bottom is another climate model, is CSM. And what you notice is that different climate model will give you different future, right? I mean, they all have things in common. So you have, of course, all of them project melting along the peninsula, which are both into those two models. And then most of them project the surface mass balance gain in East Antarctica. But then how much there's difference, right? They have similar features, but there's of course a lot of differences. And that's why I really do believe that using to make projections, it is really important to use multiple climate forcing in addition to multiple ice sheet models. Now the point of this figure was showing you how if you take one type of forcing, this is a typical climate model surface mass balance, and what happened if you downscale it using original climate model using MAR. Well, what happened is actually really fascinating because of course you have much more refined feature. That's what MAR gives you. You have more pronounced accumulation in those areas. You have also much more pronounced melting over the ice shelves. And so that's kind of important because if you think that Antarctica and ice shelves and more melt is going to be important for the collapse of ice shelves, then in a way, it is very important to capture this very narrow, those fine scale details. And so really those kind of questions, the problem is that taking original climate model does take time. It takes time to run. And then if you're using a different original climate model, maybe there might be a different solution to this plot. So it's really research that needs to be really looked into. But what I find fascinating too is that in a way, what does it mean is that having those more refined surface mass balance forcing for the ice sheets, just looking at those and how much sea level would be just simply for surface mass balance. The solid line in all cases are basically what ISMEP6 used, is directly driven from the climate model. The dashed line is how the surface measurement has changed if you were downscaling those CMIP forcing using MAR. And so you can see that after 100 years time, there is a big difference between the two of them. And in this case, in the red case, for example, using MAR meant that you would actually have much more accumulation, and so much more mass, much more mass that will mitigate your mass loss from Antarctica. So there will be mass gain from surface mass balance. Basically, that's the story. And in some other cases, for the blue line, NORISM, which is that model here, is the other way around. Basically, ISMEP6 over predicted the mass loss. I mean, the mass gain. Sorry, the surface forcing, and compared to what MAR would have given you. So those kind of questions are very important. What is the effect of climate forcing? You can think about ocean. Ocean is probably even worse. This is new research that's under review by Nico Jourdan, who was really involved in ISMEP6 forcing that we used, and it basically is comparing the calibration that we did right now for ISMEP6, which are basically those big lines, right? So the big yellow areas. Those big areas are what ISMEP6 did propose as kind of as basal melt rate. So he's comparing them with those thin lines, which are from NEMO, which is an ocean model. And he's basically coming to the conclusion that it could be that even though, I mean, it could be that we really need to revisit what we did. And that statement that I still need to digest a bit more, and I would urge all of you to read this paper when it comes out, is that, the projections suggest that this distribution of basal melt rate should be narrowed down towards lower values, and that lower parameters should be used even for reservoir projections. So it's basically kind of saying that some of these MIP6 numbers use too high basal melt rates. So as a community, it means that we really need to kind of look into those forcing and revisit what is and how to improve and do more comparison of what we did for SNP6 with the regional climate model and doing much more regional climate model runs and much more data collections. So a lot of work to be done. The other issue that we're facing as a community is that on longer timescales, this is a new effort that we're doing right now, is SNP6 300 projections. It was very hard to set up as an effort because mainly the forcing was not available from the climate models. As an ice sheet modeler, I cannot make a projections if I do not have future surface mass balance from the atmosphere or future basal melt rate from the ocean to drive my ice sheet models. And that's why this kind of conversation with the modeling community, that's the climate community that works with the polar climate, is very important. We cannot have, it's very tricky to make projections if I don't have the right forcing. So this is a surface mass balance anomaly, how it might change in the future. And what is even more important is basically how the ice shells collapse could happen due to increased surface melt in the future. And you can see that, of course, the ice shells are very susceptible to possible collapse due to increased melt. And that's one method that we did with SNP6 to estimate what those could look like. But there is a lot of research possibilities that can happen in this. When we think about, what's next, there is a lot of work. Honestly, those community efforts can only work if people take part. I know it takes a lot of time for the participant. It takes a lot of time and energy also for the leaders. So it goes both ways. But it really is important because in the end, we are kind of delivering those numbers that that will be used in IPCC report, and that will then be used with for projection and adaptations. So as a community, we have to do all that we can to improve those projections and work together. I just wanted to give you an idea again about what SNP6 is thinking of and what we're doing right now. So we are doing right now, trying to do projections at a longer time scale, to 2300. And you can still take part. And the dashed line kind of shows you again about how long it takes to plan an activity versus the solid line, how long we think it takes to run. Okay, so right now it took us about a full year to kind of get ready for Antarctica 2300. And then we are hoping that modelers can do that within 6 months. We are also focusing about improving historical simulation. This is actually really not straightforward. Thinking about what needs to happen, what are the forcing, atmospheric and ocean forcing needed in order to be able to reproduce observed changes. So that is something that we are doing. You can see that, I basically allocated another year to kind of prepare those forcing so that hopefully by mid-2023, we can have some simulations to be delivered. We really want to continue being coupled to CMIP on this climate modeling community. So right now there's talks about, there's question marks, right? Because it's not me who decides. So this is what I understand that can happen. There is possibility of CMIP 6+, which may start in 2023, which will be great because it will be a fantastic way for ice sheet modelers to test the possibilities of improved historical simulations and any improvement that we've made into understanding about parameterization. So one of the things that community effort are, like SNP6 for CRIs, is that it's really open. And so you can come to our workshops that we have, and that's what I meant by those little triangles, is that we usually have a workshop at AGU or EGU or at a big conference where we invite the community to come and give their ideas and their feedback. It seems like right now the planning that CMIP 7 may start in 2025. And so this is when the planning starts, which means that when the data will be ready for simulation would be past experience in 2027. But again, from experience, if you think about SNP 6, it began in 2014 with paper deadline in 2019, and this was a rush. And so you could actually consider that my time taken to prepare the protocol, those dashed line here, is actually not sufficient. I also want to make a highlight. So ISMIP 6 will continue being closely related to what the CIMIC model gives you. But SCAR is also leading this instant effort, which is the instabilities and threshold in Antarctica. It's a huge program that hopefully you can come and get involved with. It also is going to kind of deliver some projections, you can see on this. But those projections are going to be more based on instabilities. So what are the things that could cause the collapse of Antarctica and portion of Antarctica? So hopefully some of you will want to be involved in that too. So just in summary, understanding and projecting the Pacific ice sheets, the community challenge. I really cannot stress that you know, the only way we're going to make progress is by working as a community and not against each other. By this, working as a community, I mean that you know, what I've learned with CIRISE and ISMIP 6 is that right now the largest source of uncertainty, it really comes from the climate forcing. It comes also from knowing how to do ice-ocean interaction, the ice shelf basal melt, and of course the dynamic response to ocean forcing. This is much more an ice sheet model problem, but it includes items like knowing what a basal sliding underneath the ice sheet is. This is what's going to affect us. If you work as a community, it is possible to do actually projections for IPCC that are based on dynamical ice sheet model, which is actually really new for AR6, which is kind of crazy when you think about it. Before AR6, all of the projections, especially for Greenland, Antarctica, was basically based on a few ice sheet modeling papers, but for Greenland, it was based on temperature. So, you know, it's really important to have dynamic ice sheet models if you want to kind of capture those instabilities or capturing how the grounding line might migrate. So really, we know you can make, it's kind of crazy in a way that we are only there now, but it's amazing that we could, and there's still work to be done. It is crucial in my mind to link the CIMIP and the ice sheet communities together. It is possible, it takes time. And as we do this, we're going to see that, you know, of course, one additional research on the ocean and the atmospheric forcing. But it is really, really key. I cannot stress that for projections, because whatever I'm going to project is going to be an outcome of what I put to my models and input. I cannot stress how much observations play a role in ice sheet modeling. It's always drives the model development. We use it to initialize our model. We use it to evaluate our models. So model and observation are intertwined. It is hard as an ice sheet modelers to use observations the best, to really know how to use them properly and what their limitations are. And that's why effort like INVI is really important too, because it gives reconciled estimate that I can work with. And so this community aspect, hopefully in the future, in the next few years, is going to be the observational community working closely in collaboration with the ice sheet modeling community. Those community efforts, whether it is, you know, MIPS that will focus on the process, like the cowling milk, or whether it is something like this MIP 6 that looks at projections, or whether it is something like INVI that looks at observations. What is fascinating and what is so important for me is that they really highlight issues that all of the methods face. There are things that every study will have, and when you put them together on the same frame, this is really the only place that you can see really what's different and what's common and where things can be improved and what things we got right. So with this, I will thank you for your participation and your time. Especially if you took part in helping me become a better scientist and part of those community efforts. And hopefully, you know, I've managed to convince you that there are plenty of challenges that we need to face as a community. But if you think about how much we did with MIP 6, for example, and it's not the only MIP, right? It's just the one that I know well. You know, it is possible when we all work together to actually make huge improvements. And so with this, I will stop, and I will also stop screen sharing.
Thank you, Sophie, for excellent presentation. We have a couple of questions, but before that, I have very simple question. Is relevant to your talk today. As I mentioned today, it's very warm. The weather we have in the northern hemisphere. So the Greenland, a lot of melting is going on. Even the size of ice sheet compared to the Antarctica, the Greenland is much smaller, but maybe it has more and more impact in the future. But do you think that kind of ice melting in Greenland will continue in near future?
Yeah, it's a very, very fair question, actually. And unfortunately, so for Greenland, absolutely. I mean, Greenland is going to continue losing mass and it's really atmospheric driven. It's super clear that the more melting, that it's nothing is going to continue and it's going to become much more problematic for the ice sheets and sea level. And for Antarctica, there is a relevant to that too, right? I mean, whenever you have those warmer melt events, it really leads to water accumulating on the surface of the ice shelves and basically those possible collapse of the ice shelves. And that's an area that we don't, but I really hope that the climate models will be able to capture much more because, that's something we need to be able to take into account into our modeling. And I won't be able to take, and this is what I'm trying to kind of really bring back home is that right now, one of my limitations as a modeler when I'm doing those protocols is not so much more the ice sheet model, it is really those forcing. Like I know there can be melt on the surface of the ice shelves, but I need to have this coming from the climate modeling community. Yeah, so it's kind of a fascinating time in a way, frustrating time, fascinating time.
Okay, thank you. And there are questions from the floor that there's good question that one person asked that there are range of different models you suggest, and he asked or he or she asked how are they selected and how they compare and how they select it for accuracy, or can be select for different purpose, or what?
Oh, yeah, that's a great question. The question about fitness for purpose is actually very tricky to answer that question. I mean, there's going to be, if you ask everybody, there's going to be multiple answers. So for ISMIP6, the fitness for purpose came into multiple categories. We had the fitness for purpose for the climate models. And so for this, it was really evaluating how well the climate models were doing in the polar regions over the historical simulation, in the historical time. And that also meant that we kind of looked at a selected number of variables to see whether, for example, temperature, could they capture that? Of course, much more can be done, right? And hopefully in the future, especially as ice sheet models are being coupled into climate models, we can start having more serious discussion about what needs to matter. So for example, surface mass balance, you cannot really capture that properly if you don't have the right precipitation or if you don't have the right way of doing albedos. Albedo we can measure from space, and so there could be basically new ways of assessing the models and those fitness for purpose. So one category is the climate forcing. The other category for the ice sheet models, fitness for purpose, was basically kind of taken for granted because we know that all of the ice sheet models taking part in ISMIP6 took part in all of those previous MIP. That's why I kind of chatted and all of them had to kind of show in the past that they could do grounding line migrations adequately based on the MISMIP efforts, or they could do higher order based on how did they compare with those higher ISMIP6 higher order assessments. So we kind of did that. So we assumed the fitness for purpose. one of the parts that and we also believe that there is still a lot of unknowns in terms of key aspect of ice sheet modeling, for example, the basal sliding, or how there's some things that we don't really know how to fully do. And that's important to have so many different models. We didn't do is MIP6 a large effort of a model weighting. So this is something that we could have done, and maybe we may do in future efforts, about looking at how ice sheet models, compared to observations in the historical time or present day, and give people weight or kick them out. We started to do some of it, and I didn't show a slide, but it's very hard to do. And the reason that it's very hard is because one model might score very well if you compare to velocities, but it might compare terribly compared to ice thickness. And then the other model might compare really, really well with ice thickness and be a disaster at velocities. So those kind of questions as a community right now, we don't know how to do. It is an active area of research, and please go for it. I mean, look at it. I mean, ISME6 results are available for all to use. Address those questions, and then we can learn as a community, and therefore in the future be able to kind of say, okay, well, fitness for purpose, this model, you are not very good at this, therefore up, you out, or I give you less weight, or maybe actually, So I mean, a wide open area of research that I'm hoping that a lot of you will be inspired to do.
All right. And there is an excellent question from the floor that maybe it's come from the early career researcher on Earth. And they ask, how can they get involved in the work of ice sheet model comparison project kind of thing? How they can involve?
Yeah, it's a great question. So I know that COVID was a disaster for early career scientists and in general for research. Because I say this because in a way, my answer was going to say, well, at every AGU, at every EGU, at our very, very big meetings, we tend to advertise and prioritize that there is something going on, and that there's an event and you can come and talk. All right, honestly, we really want people to join, and we try to make those meetings at linked to conferences that we know most people attend. And that would be the simplest way. If you just want to learn and meet people, you basically kind of, when you see on prior list this kind of event and workshop, just basically sign up. ISMIP6 also has a mailing list, ismip6@gmail.com, or an email. And Pushton has a mailing list, so you can email us and ask to kind of be kept in touch. We don't send that many emails out, so the best place is still kind of looking at prior list, because we want to make sure we don't miss anyone. In SCAR and Instant, this is this other big activity. There's going to be tons of possibilities to get involved. Again, that effort, it would be a question about finding the website, and then just saying, hey, I'm interested, how can I contribute? There's always room for participation. Honestly, there's just so much work, not enough people, and it's really, I hope that you will want to be involved. For IMBY, and the observations, again, there's going to be on prior list attempt to have call for data, that it will be an email kind of saying, hey, if you have data, that kind of thing, please take part. So yes, so either keep an eye out or contact the key leaders, and then we'll make sure that you are joining the fun.
All right. I have here is some top question. Say that do you think the general public is gaining better understanding of the role of ice sheet in the future climate as a result of this work? It's probably a very tough question.
It is hard. It is hard because when I talk to people, I hear a lot of different concern and comments. Some people say, oh, but you guys are projecting there's much more sea level and we're going to kind of all be doomed, and therefore there's nothing we can do, therefore what's the point? Right. And so sometime when I give a talk, especially in Greenland, this is kind of easy, especially to show that because Greenland is very scenario dependent. So you can really make a nice story. I mean, the truth story, which is that if we reduce carbon emission right now, we can save Greenland. This is undeniable. You can do it. And it's very nice because you can say to the public, look, you can do something. We can do something. We need to do it for our kids, blah, 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 blah. Right. For Antarctica, it's much more tricky because unfortunately a warmer climate could mean more melting and collapse of more basal melting and collapse of West Antarctica, but it could also mean more snowfall and basically balancing. And that's a very, very hard message to say that it's not that we don't know and it's not that we don't try, it's just that it's messy. And the more you continue, we need to do more research. It's uncertain. We know there has been much more sea level in the past from Antarctica. We know it's possible that those rates are possible, that the observations are doing this. But yeah, it's frustrating sometimes as a modeler that we try our models really hard in SBEP6 to kind of get large sea level number and we can't. And so what do we do? Right. So this is a message that maybe I should not have said because it's going to be recorded. Maybe we should remove that part. But it's very hard as a community to, and for the general public to know how to move next. Apart from picking up all of the stone and kind of saying, if I do this, can I change it? No, I can't. Okay, right. Maybe this will work. How do I improve this? Yes, it makes, so that's really why this power of this community and being together as the same message of working to try to improve our knowledge is for me really key. Just recognizing the challenges and saying that yes, we're trying to address those.
All right, I think always modeling has some limit, but important thing is getting improved, and getting a goal forward. That's the most important thing. Okay, maybe this is the last one or two questions. So the one is come from do you see some positive consequences of a sea ice melting? That's I mean ice sheet melting. Sorry. Maybe coming close to the shore.
Exactly, my kids love the seaside, so there is a positive consequence. No, I mean no, not really. I think we can still try to stop it. I hope we can. I mean, of course, we're not going to fully stop it, but I hope we can slow it down. And then apart from basically new beach, a new seaside for my kids to play in, that's the only positive aspect. They love the sea. But even they know that this is not a very good thing for the rest of the world.
Okay, time is almost up, so I think it's the very last question to you. How much uncertainty come from the subglacial hydrology to see a sea level projection?
This is a very good question. And the answer is that there is a lot of uncertainty. We still don't fully understand how much subglacial hydrology really matters in our modeling. And but I want to say there's a lot of amazing work being done. There is some MIPS comparing different subglacial hydrology models. Those models are being coupled to the whole ice sheet models. And so hopefully you will see, like hopefully in 10 years time, all of the ice sheet models will have subglacial hydrology and we can say we've managed to move that box along the lines of what we can say that we can do. But right now it is very uncertain, absolutely.
Okay, thank you very much, Sophie, for your presentation and answering the question. And I like thanks all the participants also, and Johanna and all the technical staff behind. All the best and see you in other sessions.
Thank you.
Goodbye.